Unfortunately, the planned speaker won't be attending now, but instead of him, we have someone else from E4 Computer Engineering. She and her team were doing a groundbreaking work in astrophysical and body simulations using RISC-V-based tensor and wormhole technology, which achieved double speed up and double energy savings than compared to the improved CPU implementations, optimized CPU implementations. So please welcome Elisabetta Boella.
Hi everybody, I'm Elisabetta Boella from E4 Computer Engineering, and thank you very much for the nice introduction. Actually, it's, my boss, Daniele Gregori, was supposed to come here, but he's sick, so since I live in Asti, which is 80 kilometers from here, he sent me. But I'm very happy to be here. This is the right place, the same exact place where I got my bachelor degree and my master degree. I studied here in Politecnico, so it's nice to be here again. I'm going to present some of the work that we have done in my team about using RISC-V-based CPU and accelerators. Okay. But before starting, I would like to thank my colleague that participated that contributed to the result that I'm going to show. So Jenilyn Almerol, Fabrizio Magugliani, and Daniele Gregori from E4, and also Mario Spera from CISA, who inspired some of this work. I would like also to thank the funding agencies and the project that allow us to carry out the work that I'm going to show you today. So I would like to start by saying a few words about E4 Computer Engineering for people that don't know the company. And then I will try to reply two questions. And the first one is, are RISC-V-based CPU ready for HPC, for high-performance scientific computing? And can RISC-V accelerators speed up scientific codes? And finally, I will leave with summary and perspective. E4 Computer Engineering is a solution provider for high-performance computing, artificial intelligence, cloud computing, and now also cloud computing. We are based in Reggio Emilia, so in the Emilia-Romagna region, and we are a proud partner of RISC-V International. The company was founded in 2002, and since then the company has been involved in many Italian and European projects, included the one for that whose aim was designing the European chips based on RISC-V, so EPI and DARE. Okay, so I will try now to provide you some thought about the first question, if RISC-V CPUs are ready for HPC. And to answer to this question, so we performed a test on this machine. This machine is powered with two Sophon SG2042 CPUs, and it has the characteristics that you see there. And the SG2042 is a RISC-V CPU, which was aimed for one of the first CPUs that was based on RISC-V, aimed for high-performance computing. So with this machine, we carried out tests using legacy codes, so codes that were developed and are currently used for science. In particular, in this case, I'm showing you the result obtained using the code Siesta. Siesta is a code for molecular dynamics. It's part of the MAX Center of Excellence. MAX stands for Material at the Exascales. where the aim is basically further developing this a bunch of code for molecular dynamics to study material and to adapt them for exascale. In particular, Siesta is written in Fortran. Yes, they still exist, code written in Fortran, especially in physics, and is parallelized with MPI and OpenMP, and relies on a bunch of libraries like BLAST, LAPACK, ScalaPack, and ELSI. We perform tests with this code on the machine that I showed you before, and we compare the result with other server powered by CPU based on x86 or ARM. For this test, we used the use cases called Quantum Dot, and the code was compiled with the new compilers and Open 13.2.1, and then all based on that, and OpenMPI 4.1.4. I just would like to point the flags that were used. So this machine has a vector extension. The SG2042 is equipped with a vector extension 0RVV 0.7, but the new compiler does not support it. Indeed, this was the flag used passed to -m arc, where no vector extension appear. In the first plot, in the middle of the slide, I reported the wall time execution versus the number of MPI tasks used, of physical core used, basically. And I would like to focus on the red curve that corresponds to the Sophon SG2042, while the other color are tests performed on AMD Genoa and on other two, or on Ampere Ultramax and NVIDIA Grace, so x86 and ARM. What we can see is that, unfortunately, the time obtained on the SG2042 are still higher than the competitors, about one order of magnitude higher. But the fact that we could almost easily compile the code and run it, and the results were correct for us, was already a very good result. What we can also see is that the time increasing the number of MPI tasks launched, but at a certain point at around 32 MPI tasks, the curve flattened. And when using both socket, so when passing from 64 to 128, we observe actually an increase in time. And this points out to memory issues of the processor. With the wall time, we could compute the parallel speed up in what is substantially a strong scaling test, and this is reported on the right plot. I want to ask you to focus again on the red curve and to compare it with the black one, which is the ideal speed up. What we can see is that there is a superlinear speed up from 1 to almost 16 cores, which again might be to the memory, and then the curve again flattened with the speed up decreasing, passing from 64 to 128. This was not the only test done. We also tested on the machine OpenFOAM. OpenFOAM is a very old code for computational fluid dynamics. Is written in C++ and parallelized with the MPI. In this case, we model the lead-driven cavity flow, and we launched the simulation with two types of grid: a smaller grid of 1 million cells and a larger grid with 8 million cells. And again, we launched the same simulation with 32, 64, and 128 cores. So until 64 cores is one socket, and passing to 128 is the two sockets. And again, we observed that the performance decreased with the wall time going above the baseline using 128 processors. So we think that this is due to issues with the memory. This concludes more or less what I wanted to show you about CPU. Again, the point is that, okay, maybe performance is still not optimal, but the code ran, the results were solid, and it was the code compile almost easily. So these are all good news that points us to the maturity of the software stack. Then the second question I would like to reply to is, can RISC-V accelerator speed up scientific code? For this, what we did was to port n-body code on the wormhole N300 accelerator. This is an accelerator developed by TensorRent based on RISC-V instruction set architecture. So here on the left, you have a picture of the accelerator. Each accelerator has two chips. The first chip is connected through PCI Express to the CPU, to the host, while the second chip is connected to the first chip via Ethernet link. Each chip has 64 10⁶ core. A 10⁶ core is basically the compute horsepower of the accelerator. And on the right, there is an image of a scheme of the 10⁶ core. So each 10⁶ core is equipped with 5 baby RISC-V cores, 2 for data movement and 3 for computing. Each chip has a SRAM, so the data movement baby RISC-V cores, their task is to move data from the off-chip DRAM to the SRAM, back and forth. While the compute core, basically, they issue instruction to move the data from the SRAM or to the SRAM, and then the RISC-V baby core in the middle is the one that issue compute instruction to the tensor unit or to the vector unit. So another things that we have to notice here is that the tensor unit the tensor unit, the FPU, work in reduced precision up to FP16, while the SFPU, the vector unit, is a sort of CMD, works in single precision, so up to FP32. I just mentioned this because this is important for the code that we developed. So as I said, to do that, to test this RISC-V accelerator, we have developed an n-body code, and we ported the most computationally expensive kernel to the accelerator, and we did this with the TensorRent API TT Metallium. In the end, this is an n-body code for that compute the interaction between celestial bodies, basically, so the gravitational force. The formula of the gravitational force is there in the slide, and this is coded with this is classically coded with 2 for loops, 2 nested for loop, and we parallelize the outer for loop, so the loop over the particle for which the force is computed. And the plot on the left, the image on the left, try to express this. And in the case of 2 10⁶ core, imagine core 0 and core 1, each of the core receives a bunch of particles. We pass, in general, 1024 particles because this is the size of the tiles, the memory layout that the TensorRent uses. So there are 2 nested for loop, and the inner and to compute the force on each particle, basically you need the information over all the other 1024 particles. So we need to pass the data also to of this other particle, and we do this copying the information of all the rest of the particles and organize them in tiles that contain basically 124 copies of the same particle. So computation happens in parallel, and the force is accumulated along the row at the end. And like each column are computation that occurs in parallel, basically. On the right, what with this image, I just want to show you how the overlap between computation and data movement occur inside the tense torrent accelerator. So while basically the instructions are pipelined and there is an overlap between data movement and computation, which makes this chip good for HPC, for basically scientific computation, parallel computation. So here I want to show you some of the results that we achieved. In particular, we compare the performance of the accelerated code versus the performance of the same code but on CPU. And for this, we use a version of the code that is parallelized with OpenMP, and on top of that uses AVX 512 intrinsics to compute the force in single precision. So this code is basically a parallel of the accelerated code and works also in mixed precision, like the accelerated code. So on the left, what we have is the wall time, the execution time, the distribution of the execution time over 50 simulation of the accelerated code, while on the right we have the same but for the code that run on CPU. For the CPU code, which we call the golden reference, we utilize basically the whole hosting system, which had 32 physical core. It was an MD Genoa, dual socket MD Genoa. The red line is the average time. What we can see is that in average, an accelerated simulation using the test torrent took about 300 seconds, while the same simulation on CPU took in average 672 seconds. So with the RISC-V accelerator, we got about twice the speed up than on x86. We also monitor the power consumption and in order to compute the energy consumption of our simulations. What I plotted here is the time history of the power on the left of the tense torrent cards during a typical run. In particular, the one at the most left is for a simulation that utilizes one of the 4 cards available in our server. On the right, instead, is for the simulation that run on CPU. What we can see is that, okay, for the simulation that run in CPU, the cards remain idle and the power is about 10 watt the power absorbed is 10 watt per card. On the left, what we can notice is that after a sleep, the simulation start, which is the black vertical line. There is an initialization phase which occurs on CPU, and then the red curve, you see spikes. This is the power absorbed by the card that is used. And we see that it oscillates at around 30 watt, and the peak are when the kernel is called and the computation occurs on the accelerator, and the lowest point are where the minimum are when the CPU is working, basically for the computation that are run on CPU only. We can see that all the 4 cards are initialized, and so their power increase, even though we in this type of test we use only 1 card out of the 4. We then look also at the power absorbed by the whole system, so excluded the RAM and the net and the other things, and this is plotted on the right, on the black curve, where again we have on the left the time history of the power for a typical simulation that uses the accelerator, while on the right for a typical simulation on CPU. What we can see is that, of course, this, as I said before, the simulation of the CPU take much less time, but the power absorbed by the system is slightly increased with respect to the simulation that run only on the CPU, because the cards are working and they absorb power. We use this data to compute the energy, the average energy for the simulation. And again, we did a statistical study over 50 simulation run using the accelerator and 50 simulation run only on CPU. With the golden reference version of the code. And results are reported here, where on the y-axis we have the number of simulations versus the energy absorbed. In red again is the average energy absorbed during these 50 simulations. What we can see is that the accelerated code on average consumes about 70 kilojoule, while the code running on CPU absorb an average 128 kilojoules, so almost the double. With the RISC-V-based accelerator, we were able to, the simulation were much more sustainable, and we were able to save energy. Finally, we also scaled our code to run on more than one card. Here I reported the results. We implemented two strategies, one using only one chip per card, which is the green one, the green curve, and the other strategy using both chip per card. So, and we were able to scale to use the 4 cards that we had in our system, binding each card to one MPI task. So on the plot on the left, we have the time to solution versus number of MPI tasks. Keep in mind that for the green curve, this means 4 chips, while for the orange curve, this means 8 chips. What we can see is that the green curve, which correspond to the approach multi-host single chip, so only one chip per card, show a shorter time to solution than the other approach using the 2 chips. In this case, because the Ethernet link between the two chips basically act as a bottlenecks, and we have to move data, and this require time. With this, we can see also that the scalability, more or less the time increases the number of MPI tasks, increases the number of cards and number of chips is similar, and this is indeed confirmed by the parallel speed up, which is plotted on the right, where we can see that there is a speed up passing from 1 to 2 and from 2 to 4, though is far than ideal, very far from ideal, which means that we need to work more on the code to optimize the code better. But nevertheless, for us was a very nice result, because this is the first example of a scientific code which can run using more than one RISC-V accelerator. So I leave now with the conclusion. So we have performed tests using RISC-V CPUs with the legacy code. We observed that the time, the execution time is usually 1 order of magnitude longer than on more established architecture. Nevertheless, for us, these were a positive result, because we were, the fact that we could compile this legacy code written like in the 80s or the 90s, and they could run and provide the correct result, and we could compile even all their dependency easily, was point out to the maturity of the software stack. And we then ported an n-body simulation code to RISC-V-based tenstorrent accelerator, and in that case we observe a 2x speed up in comparison to CPU, and also a almost 2x energy efficiency in comparison to CPU. Finally, we managed to scale our code through using multiple tenstorrent cards, and this is the first example, at least to our knowledge, of scientific code able to use more than one tenstorrent RISC-V-based accelerator. For next step, we want to redo the test with a newer version of the CPU, the SG2044. Which has a vector extension, not 1.0, and the new compiler hopefully support it. And then we have to, as I show you, the scalability of our n-body code was awful, so we have to work to improve the scalability. And finally, we want to test the same code on the new model of the tenstorrent accelerator, the P150. And this concludes my talk.